Okay, so this is a review for a lot of y'all, but for Anthony it's his start. So what we're going to look at is just the basic electricity for this class, enough so we can make sure we have enough knowledge to do this class. So we got a little pretest. So what is an electrical circuit? What is a conductor? What is an insulator? What natural metal is the best conductor of electricity? What are the two most often used electrical conductors? What's voltage, current, and resistance, and power? A lot of times we get so involved with voltage and current we forget what power is, the importance of power. What is the difference between DC and AC? Of course, in cables, especially on metal cables, we can either use direct current or alternating current. When we get into alternating current, we need to understand what a cycle is in frequency in a hertz. We need to understand the difference between an open and a short. Short is probably one of the most misused words not in our trade, but people who don't understand the trade. What's requirements for a basic circuit? What is the difference between a series and parallel circuit and a series parallel? I don't know about that. The difference between resistance and reactance, it's really important that we understand that. Is everybody here at AC? Except I know Anthony had. The difference between reactance and resistance, which really comes into consideration when we start dealing with conductors that handle communication, and the difference between true power and apparent power. So some of y'all, hopefully, if you're been in these before, y'all should know all this, but this is all covered inside this lecture, so we're not going to answer this question. These are conductors. Most of the time when we ask what's the best electrical conductor, what would you think? Anthony, right? What would you think the best electrical conductor would be? Conductor of electricity. So we go through metals. It's going to be, the conductors are going to be metals, right? So what metal would you think would be the best electrical conductor? These guys should know, so that's why I'm asking you. Of course, you're looking at the thing. Copper is not the best. Silver is actually the best. So of the known metals, silver is the best conductor of electricity, followed closely by copper, annealed copper, which is still copper, gold, aluminum, and then they drop down into non-metals, seawater, drinking water, and air. You can see airs are really good. And the smaller the number up here, the better, the bigger this number is right here, the better the conductor, right? So this is what we call in Siemens. So silver is the best conductor, copper is the second best, followed by gold, followed by aluminum. What's the most widely used? What's the two most widely used? That would be up in the air. Two most widely used. Yeah, copper and aluminum. You can't say copper because think about what we call the high tension lines out there. All these high power lines from Alabama Power, those are all aluminum. Every one of them is aluminum. For years and years and years, silicon, which is a semiconductor, was the main building block for all integrated circuits. So all your processors, all your computers, all those little square blocks you see inside a computer could not use copper because copper would eat up. I mean, silicon would eat up copper. So if we tried to put conductors on the silicon that were made out of copper, it would eat it up. So for years they went out and all the conductors inside of every IC you saw was made out of aluminum. They finally figured out how to do it. Intel figured out how to do it. They came out with a processor they called the Coppermine, which I think was the 386, or they figured out a coating they could put on top of the silicone, which it wasn't either copper. And of course, since then they've been using copper. These two are widely used, copper and then aluminum. Silver is the best. We commonly use silver for a plate. So sometimes when we got a light switch or any type of circuit that makes by touching two conductors together. So when you have a light switch, that's what you're doing. If you ever look inside a light switch, is you got one conductor on this side and another conductor on that side, and all you're doing is touching them together. Well, what we want there is we want an extremely low resistance contact. So if you ever take apart a light switch and you look at the two little things that make contact with each other, they're either going to be they're going to be gray because silver oxidizes. That's why, because but we don't use silver as the primary conductor. What we do is we take copper and then we plate it with silver. Plating is a process where we can take a metal and charge it to one potential, and then take another metal and dip it in an acid vat and charge it to another, and then the molecules of the metal come up here and migrate or adhere to the metal that we're trying to do. Like chrome. Chrome's a perfect example. Your bumper is not made out of chrome. Your bumper is probably made out of steel, right? Well, how did they get that chrome on there? Well, they electroplate it. Chrome don't get along with steel, by the way. Chrome gets along with nickel. And nickel gets along with steel. So if you ever see them chrome something, first of all is they nickel plate it, and then they do what? Then they chrome plate it. But they do it by what we call plating or electrolysis. Copper is extremely good, so we use this a lot. Gold is very good, but it's not extremely good. So we don't use gold. We use it as a plate. Now, one advantage that gold has over other metals is the rate of oxidation or corrosion, rusting. Gold don't rust. So anything but copper does. Copper oxide, silver's pretty neat in that oxide, silver rust is as good a conductor as silver. So a lot of times you'll take like a relay apart and you'll look at the contacts and they look all gray, and people will try to clean them off. But those are silver plated, and what happens? Well, they'll get a file and they'll file them off, and they get down to the copper. Copper oxide is an insulator. So what happens now, you file those contacts off, they work for a while, then after a while they stop working, because if you file them down and get down to the copper, then what's going to happen? Well, the copper is going to rust, and copper oxide is an insulator. Gold basically doesn't oxide. But gold gets along with copper real well, so what we'll do is we'll have a copper conductor, and then what will they do? They'll gold plate it. So a lot of printed circuit boards that you see that goes into an edge card either do. So the amount of work we get is force divided by distance. Distance and speed are what we call inversely proportional. So we also could cancellate it by how much force we're exerting times the speed that we move things at. And this is basic work. So in electricity, we call it power, and this is the formula we use right here. Our force is going to be in something that we refer to as volts, and our speed is going to be in what we refer to as current. So to get electrical work, we got to have two things. What do we got to have? We got to have a push, right? You understand? And then we got to have speed. Does that make sense? So it's just like a track star, and they're trying to perform work. Well, are different people. They get out there and they walk around the track, or they run around the track. Who's going to create the most work? Purple walking or the people running? Running. But you could create the same amount of work. It's just that if I drop the force down, so let's say I half my force, but I double my speed, right? You understand that? Understand what I'm saying? Then you would end up doing the same amount of work. Now they're dealing with this right here. Okay. So what we do in electricity or electronics is we're going to be dealing with this guy right here. So that means if I half the voltage, but I double the current, it would do the same amount of work, right? You understand that? Or if I double the voltage, I could half the current and do the same amount of work. The amount of current controlled by the amount of voltage and the amount of resistance, and we'll talk about the amount of current is controlled by the amount of push and the amount of resistance. And we're going to look at resistance here in a minute. Are we okay? We're okay so far. Electrical current consists of an atom's electrons that have been forced to move by a difference of electrical potential. So what we're doing is we're taking atoms and we're applying a force, and then we're causing these electrons to move. And that's what current is. It's the movement of electrons. But before we have motion, we got to have force. Everybody okay? Makes sense? So I've got a perfectly flat surface, and I've got a car sitting out there. What's that car going to do? It'll sit there, right? So why do we make it move? How do we make it move? We apply force. We can do it one of two ways. We can apply force with the motor right in there, or we can push the car. And of course, once you got the car in motion, then what determines how fast it goes, of course, would be the opposition that the force is pushing against. Right? That makes sense. The strength of the difference of electrical potential and the amount of opposition that flows. Opposition to the flow of electrons determines at what speed the electrons move. So that's exactly like a car. So what determines how fast a car goes? What determines how fast a car goes? And the force or the weight of the car, right? You understand? So this is why big cars get less gas mileage than what? Small cars. You don't understand because they're pushing more what? They're pushing more weight or having, so that weight is your opposition. But the car don't move if the car is not there. So what we're saying, to do work, you got to have a force. If you don't have a force and you're not pushing that force against something, then you don't do any work. Well, force is work, right? So what is force? What's the difference between a pressure and a force? What's the difference between a pressure and a force? So if I was to get my voltmeter and I was to put it across that wall outlet there, what's my meter measuring? We say it's voltage, but that voltage is a pressure. But that outlet there is not doing any work at all. Y'all understand that? All it is a pressure. What do you need to do? Well, what you need to do is a force requires a pressure. But a force is something that will cause the shape of an object to change, or will cause the direction of an object to change, or will cause that object to move. That's what a force is, right? You understand? So force is pressure in motion. Everybody understand that? We can't have a force without a what? Without a pressure. And the main formula that we use to calculate force, anybody know what it is? Equals to, and I don't know why I put R out there, I'm sorry. This is a basic formula. is equal to pressure times the area that you're pushing. That's what force is. So that means you got this, let's say I got 200 pounds of force up here. And I go out there and I try to push a 200-pound car and I try to use one thing. Am I going to be able to push it? Because that's 200 pounds, but that 200 pounds is only pushing against that one little area of my hand. So what do? I might put one hand up there and I still can't push it, right? You understand? I put two hands up there, now I can't push it. I'm not changing the force. What am I changing? I'm changing the area. I'm sorry, I'm not changing the pressure, I'm changing the area. If I change the area, then I can change the force. But we have to have a force, we got to have opposition, right? If we have no opposition, then we have no work. Everybody understand that? So we have to have opposition in a circuit. This stuff called reactance and resistance, these are the guys that actually do the work in the circuit. Some materials such as metals allows electrons to move freely, while others such as rubbers do not. For these reasons, most metals make good electrical conductors. We didn't say all. We said most make pretty good electrical conductors. And then we have other materials that make good what we call insulators. These are rubber, paper, ceramic, Teflon. There's all types of things that we call insulators. So voltage is a difference in electrical potential. So there's your pressure that forces electrons to move. Current is the flow of electrons that is the result of a difference in electrical potential. Everybody okay? And then resistance or reactance are opposition to current flow. And we'll look at this more later on. So resistance is something that does not vary with frequency. Reactance is something that varies with frequency. We need to learn what frequency is before we'll look at this more in detail later. So what is our conductors carrying? Well, our conductors are carrying this guy right here. Current. But to carry current, we had to have a what? We had a voltage. And then that current, the conductor is going to get us from the source of the pressure, we call them power sources, to the load that does the work. So conductors don't do electrical work. They're not supposed to, they do. So electrical circuit is a complete path for current flow. So to get work, we got to have a circuit. A circuit, we got to have a complete path for current. The basic part of a circuit, this is very, very basic. We got to have a voltage source. Some people call them power sources. We got to have a source conductor. We got to have a load, and we got to have a return conductor. And of course, a good analogy of a circuit is a human circulatory system. So what do we got? What's the source of our pressure? Nope. What's the source of our pressure? What's the source of our pressure? What's the source of our pressure? Nobody knows what the source of your pressure is. Your heart is the source of your pressure. That is the heart. Oh, I didn't hear you. Yeah, the heart is the source of our pressure. Okay. And what's the loads? Yeah, what's the loads in the human body? Bones. We use it, not the bone, huh? Huh? Well, muscles. All your muscles. Your lungs would not work without muscles, right? So your lungs has a job to do, but what makes you breathe? The lungs don't make you breathe. Muscles. What makes your arms move? Muscles. What makes the heart beat? Muscles, right? Y'all understand that? So the loads that our blood is providing nourishment to is our muscles. So that's where the blood vessels go. The blood vessel goes out to muscles. Carries two things. What does it carry? What do they carry? Y'all know what carries? What's in the blood? Two things. Of course, not the hemoglobin, all that other kind of stuff. But the main thing they carry, of course, is oxygen, right? And then nutrients. That's what it's transporting. Of course, there's a lot of other stuff in there. But we send it out. The heart creates a difference in potential, which would be similar to our voltage source, which causes blood to flow. The blood flows through arteries and veins, right? We generically call them vessels. We send the blood out, it goes through the muscles, and then what does it do? Returns back, right? Everybody understand that? So we have to have source conductors, which would be the arteries. We have return conductors, which would be the veins. And of course here they indicate the arteries and the veins by, blue is the veins, the red's arteries, here's the heart, and of course they go to every muscle in the body. And what happens when you lose your blood flow? You die, right? An electrical circuit works similar to a human circulatory system. The heart pumps blood out through the arteries, through muscles, and then back to the blood back through veins to the heart. Voltage source is similar to the heart, right? It pumps and pushes electrical current through the electrical loads, which are the muscles, right? It pulls the electrical current back. Electrical current is similar to the what? The blood flowing through the body. Conductors are similar to your blood vessels. All they are just tubes that carry the liquid blood to your muscles and then brings it back, right? And every once in a while they have to be spliced. Ever had a blood vessel spliced? They terminate, we don't turn. Muscles are similar to electrical loads. Electrical loads are devices that use the current to perform work. So this is basic electrical circuit. We see this all the time. And normally, so where's our conductors at? So what's the function of the conductors? Carry current, right? That's what they are. That's what they're in there in life. That's the only function they have in life. They do not do any work. People get confused with what work is. So work is when we actually create power. Conductors, they're not supposed to create any work. If they do create a lot of work, then that's going to give us problems. So we have a voltage source. Here we have a battery. And what's it doing? It's creating a what? Pressure. We call it a difference in electrical potential. We have something that pressure can push against. What's it pushing against? The lamp, the resistance of the lamp, right? You understand. Now we can create work. Because power is equal to what? Force times, power is equal to V, and what does V stand for? Volts, times I. I is the abbreviation we use for current. That's the main power formula for electricity right there. V times I. So if we don't have pressure, we don't have current. And we got to push that current, we got to push that pressure against something. How much opposition that guy right there has and how much push we have determines the speed of the current. That current is speed. Everybody okay? Any questions? Basic circuit. Now normally we add some type of control device in here. We call it, that's a symbol for a switch. And now this is a basic flashlight. So your light switch, what you can do with the flashlight, turn it off and turn it on. Voltage source. Electrical load, source conductor, return conductor. If we don't have any of these components, we don't have a circuit. So I can take the bulb of a flashlight and I can hold it in my hand. And I can take a battery and hold it in my hand. What happens? What are we missing? The conductors, right? If I lose one conductor, it don't work. If I don't have the light, it don't work. If I don't have the battery, it don't work. So you got to have all these three components to create what we call a circuit. Flowing through the load produces work. So we don't get work unless we have a load. All circuits fall into one of three categories. We have what we call series circuits, parallel circuits, and series parallel circuits. Now what we're talking about here is not, these are how we connect the loads. The series circuit, all the loads are being powered by a voltage source are connected in one after the other. The voltage provided by the source is distributed across the loads proportional to the load's opposition. Since there is only one path, the current through each load is the same throughout the circuit. So this would be an example of a series circuit. Now, electronic circuits are either going to be parallel, or predominantly what we call series parallel. Power distribution is done in parallel. We'll look at that in a second. So if you work inside a stereo amplifier or something like that, you're going to see a lot of these guys. If you work for Alabama Power, you're going to see parallel circuits. Or if you work in the electrical trade, you'll see parallel circuits. But you need to understand them. So what we have here, these are our conductors. Right here. This is a conductor. This is a conductor. This is a conductor. This is a conductor. And this is the return conductor. For DC, this right here would be the source for this circuit right here. So what happens, the current leaves the source. Now what happens every time we push current through something, so I'm going to push current through this guy right here. Now voltage does not move. I don't know why it's not letting me draw that. So ink. I think I know what it's doing. So when current flows through this, it flows to an opposition. So let's say we've got, let's say we got 8 volts of push. So when you look at voltage, that's what they're defining. They're defining how much push we have. So the higher the voltage, the more push you have. Does that make sense? Now let's assume all these have the same amount of opposition. Well, what happens anytime I go through opposition, we lose pressure. So that means if I had the ability to measure my pressure right here, and we do what we call a voltmeter, if I went across here, it would measure 8 volts. And if I measure across here, it might show 6 volts. Well, the voltage is not moving. Y'all understand that voltage does not move. What's moving is current. But when the current passes through a load, it does what? We lose some of our push. And we call that a voltage drop. So if I put my meter right here, it's going to measure 2 volts, which means I had a watt across that device. I had a 2 volt drop. So we lose pressure, right? Does that make sense? Now how much work this guy does, we would say this would be, power would be equal to 2. That's how much it drops times whatever current we have. And that would give us the work that that device is performing. Now if they had all the same apposition, Then if I went right here, what would it measure? Here it would measure 4 volts. Because that would be, this guy's dropping what? 2 volts. This guy's dropping 2 volts. Okay. Then if I measure right here, it's going to measure what? 2 volts. And if I measure right there, it's going to measure 0. Because now I've got my meter at the same place. So one of the rules of a series circuit is all the voltage is dropped, has to be dropped within that circuit. Now the problem we have is that if this load right here goes bad and current doesn't flow through it anymore, then this guy right here is not going to do any more work. So if you've got Christmas lights are hooked in groups series. What happens if one of your bulbs blow out? They all go out. Why? Because they're hooked in series. But instead of me having a big old bulb that's rated at 120 volts, I can have a lot of small bulbs that might be rated at 8 volts, right? You understand? And then I put, how many would that be? Let's do 4 volts. That'll be easy to calculate. If I put 30 of them in series, then every one of them would drop 120 volts. So that's why if one of them goes out and you short it out, all the rest of them get a little brighter and they'll start going out, because now instead of dropping 4 volts, they're dropping more volts, right? You understand? So that's the biggest disadvantage of a series circuit. It allows us to use loads that are rated at a lower voltage, but if one of them goes out, that means they all do what? They all go out. That makes sense? So we do this a lot. So Christmas lights, a perfect example. Christmas lights are what we call a series parallel circuit. They used to be series. And if you lost one bulb, they all went out, and then how do you troubleshoot them? Get a good bulb and do what? Move them down the line until you figure out which one. Of course, there is an easier way. With one of those voltage detectors. This is a parallel circuit. This is the way power is delivered. This is the way all your outlets are delivered. The voltage applied to each load is the same. All loads are connected across the voltage source. The current is distributed in the circuit inversely proportional to the branch. So this is a parallel circuit. So notice all the loads are connected across the voltage. This is the way your house is wired. So if this right here is 120 volts, then all your loads are going to have to be able to handle 120 volts of push. You know, that'd be like having a string. Push can be a force, but it also could be this way, right? So I got a string that can handle 60 pounds of pressure. Well, what would happen if I got 120? It's going to do what? It's going to break. So all your loads are rated at a certain amount of voltage. So it means I can't take a light bulb, a regular light bulb that's rated at 115 volts and hook it up to my car battery. Or I couldn't take a light bulb that's rated at 115 volts and put it on 240 volts. If I put it on 240 volts, it's going to burn up instantly. It's going to blow instantly. If I put it across my car battery, it's not going to create enough power for me to even do what? Yeah, it's going to, but we can't see it. So loads are usually rated at what voltage they're designed to run at. So if I was to take one of those little old light bulbs out of a series string and put it across 120 volts, it's going to blow instantly, right? Now what's nice about parallel circuits is I can do this. I can take this load away and all of them still see what? All of them still see 120 volts. I could come up here and I could add another load, and it's not going to affect any of the loads in the circuit. So that's why in your house, what can you do? You can turn lights on. You can do what? You can turn them off. You can plug hair dryers in and turn them on, turn them off. You know, you can plug in vacuum cleaners, turn them on, turn them off, and it doesn't cause your lights to go out. If your house was wired in series, then everything would have to be turned on. If you ever turned off your light, everything in your whole house would go off. Does that make sense? So parallel, this is the way power is distributed. Power is distributed in parallel, but we still have to have what? We still have to have conductors, and we still have to figure out how we connect all of these together. If I went into my breaker box and I looked on the side right here, I have one wire running out. I might have 15 plugs out there, but I only have how many wires? One. Well, what we have to do is figure out how we do all our jumping and hook them out in parallel out in the house, not at the panel. Series parallel, this is the way most Christmas lights are wired at now. In a series parallel circuit, some of the loads are in parallel and some of the loads are in series. So this would be an example of a series parallel circuit. This is basically the way Christmas lights are wired now. In the old days, they were strictly series, but now they're usually series parallel. So what happens if one of your bulbs go out, you just lose a section of your lights, right? You don't lose all 500 bulbs. This is what most electronic circuits right here are parallel. But we still have to get what? We still have to figure out how to run these conductors, how to terminate them, maybe splice them. Another thing that we need to understand, go ahead and take a minute break. Somebody tried to call me. Okay, symbols of the trade. Similar to road map, the schematic is a graphical representation of electronic circuit using a set of symbols. So the sum of symbols we'll see, of course, is so if I'm hooking up wires, you know, we got to know what to hook them up, right? This is a symbol. In fact, they're going to pop up there, but this is a symbol for what? Yeah. Well, the DC, it is a DC source. It's just that a battery is a DC source, right? This is a symbol for what? AC source. This is a symbol for a, resistor. This is a symbol for a connection. What's this a symbol for? Yeah, this is a symbol for something called an inductor. And why does it have that symbol? So this is an inductor right here. So it's just nothing but wire. Just coils of wire, that's all an inductor is. This is a symbol of a device we call a capacitor. And we're going to have to look at these. These don't really come into play that much in power cables. When we start dealing with communication cables, these guys are very, very, very important to understand those. This is a symbol for what? Transformer. What does a transformer do for us? No, don't step up or step down power. Voltage, yeah, don't change. If it was an ideal transformer, it wouldn't change the power at all. But it does just a little. This is a symbol for well, usually when we see the two dots, it would be a single pole double throw. But usually they put the lines up there. This is a symbol for a ground. This is a ground. We have a different symbol for common. This is usually misused though. This is a pretty standard symbol. So you're right, but it's not technically right. And this is a symbol for what? What? A fuse. That's a symbol for a fuse. So DC voltage source, AC voltage source, something called a resistor. This is a load that we use sometimes. Some devices use resistors. So electric heaters, if you got an electric heater, that's all that is a resistor. If you got a toaster, that's a resistor in there that's getting real hot. So the work that a resistor does, it drops a voltage for us. Normally we say they control the flow of the current. This is a connection. This is a device called an inductor, which we'll run into in this class. This is a device called a capacitor, which we'll have to understand for this class. This is a transformer, which changes voltage for us. This is what we call a single pole double throw switch. Normally a single pole switch wouldn't have the other dot up there. This is a common, but that's not really true. That's a symbol for a ground. I need to go back and change that. And this is a symbol for a fuse. This is a print or a drawing of a commercial building, I believe. This is one of the prints that if you're in the electrical course, you'll be dealing with in the commercial wiring class. And of course, all these are different devices. These are our loads right here. So before this makes any sense to me, what do I need to know? I need to know the symbols. If I don't know the symbols, then this right here don't make any sense to me. And if you hadn't had the commercial wiring class, then this right here doesn't make any sense to you at all. Okay. But these wires right here, these are your conductors. And sometimes they put how many conductors there's running in the cable or in there. These are lights. These are outlets. So those are wall outlets. The S's. What do you think the S's are? Can y'all see any S's on here? They're hard to see. I know the print's not big. These are pretty big when you get them in your book. But S's is the symbol they use for a switch. So they'll see put an S on the wall. That means that's a watt. That's a wall switch. There's a symbol for a true light. They don't call them lights. This is the symbol, what they call a luminary. And it's not actually the symbol for the light. It's the symbol for the socket that the light goes in, which is pretty interesting. But this is, of course, these are walls, and this is glass, and these are outlets right here. And so these are all wall outlets. And it's got, if you can see, it's got a little 4 out. What does the 4 mean? Anybody know? Nobody's here at commercial wire. Well, if you look in your panel box, what most people call a breaker box, every breaker's got a what? A number. Well, that tells you what circuit that those wall outlets hook up to. So the electrician that would run this would know to hook all these things there. When they ran them through the wall, they would know to connect it to which breaker in the panel box. Breaker number 4. Voltage is, and so we're going to have to learn symbols. I mean, it's just that simple to understand. This class, we don't have a lot of symbols. We have our main symbols, and I didn't put the main symbol up here in this class. This is symbol right here. What's this symbol right here represent? Yeah, this represents the conductor. And that's pretty standard in all trades. I mean, all electrical trades, excuse me. So what is voltage? Should be pressure, but most people call it a force, but it actually is a pressure. Because we don't have a force until that voltage does what? Well, it's got to push against something. It's got to push against something. Pushes current, that's right. So it pushes current, but it's got to push it through something, right? You understand? So it's got to push that current through something. And to get to that something, we have conductors. So we use V to represent voltage, or we use E to represent voltage. And the unit, by the way, is the volt. So the term voltage is basically talking about the push, and the unit is what we're going to call is a volt. So the push, when we deal with the math formulas, the voltage could be represented by V or E, but the volts are always represented by the letter V. So we say we have 120 volts. Well, we have meters that measure, we call them voltmeters, and what do they measure? They measure the difference of electrical potential, and they measure volts. Amperage, most people call this amps, is the measure of the amount of current that is flowing, and it is the speed, by the way. So amperage is what you're doing is you're getting an indication of the speed. So when we look at our car, over here it's rated in miles per hour, right? You understand? Well, in the current flow, we're talking about electrons per second. So 1 ampere is equal to 6.25, and that's rounded, times 10 to the 18th electrons. And that's this number right here. Moving past a point in a circuit in 1 second. In math formulas, current is represented by the letter I. So some books might say that V is equal to I times R, or some books might teach V is equal to I times R. Now, the problem with this is that current is in amps. Amperes is technical. But in the math formula, we use I to represent ampere. Okay? Makes sense? So using V on the left side and solving for V on the right side on this formula right here, some people don't like that. So instead of using V is equal to I times R, they use Y. And both those are the same. So some books teach E for voltage. Some books teach V for voltage. Who's correct? Both of them. In the military, we learned E when we took it. Resistance and reactance are the measure of the amount of opposition to the current flow. The unit of opposition is called the ohm. So some people spell out ohms. We don't write O out there because it looks a lot like 0. So normally, if you're good enough, after a while you learn how to draw that guy. All devices exhibit opposition to the flow of current. Conductors have almost no opposition. So right now I'm moving my hand through the air and I feel no opposition at all because of my speed, right? You understand? But we got these supersonic planes, we got meteorites that come into the atmosphere, and what do? They burn up because they're moving at such a high rate of speed. So even though the opposition is very low, if you create a high speed, you create a lot of work, right? You understand? So this is why, these extremely high speed planes, like the SR-71, had to have special. And what happened to the shuttle, the Columbia, that burned up? Got a little hole in one of their ceramic tiles that blocks all that heat, and it came through and got into that aluminum, and what did it do? It just melted. Because power is equal to force times speed. So your force might be very, very low, but if your speed is extremely fast, then you can still create a lot of power. Conductors have almost no opposition, while the opposition of a load is considerably high. Insulators have extremely high opposition. So in formulas, resistance is represented by the letter R, while reactance is represented by what we call X of C or X of L, which we'll talk a little bit when we start talking about what's going on in a conductor and what's going on in the insulator. People don't really understand that. And so that's what we're going to learn here. We're going to learn about the actual conductors themselves so we can understand why things are the way they are. So 1 volt will push 1 ampere of current through 1 ohm of resistance. So the formula is for V is equal to I times, So V is equal to I times ohms is what's true right here. And notice they're on top. Anything that's on top of a fraction is what we call directly proportional. So that means voltage is directly proportional to current. So that means if I double the voltage and I don't change the resistance, what's going to happen to the current? It's going to double. If you half the voltage, the current's going to half. Ohms is equal to voltage divided by current, which should make sense. And I is equal to V over ohms. And of course, in DC you learn this, but we've added these guys right here. And all these are rated in something that we call ohms. So it don't make any difference. The amount of current you get is equal to how much push you got divided by the opposition. So up here, opposition is on the bottom. So I is equal to V over ohms. Or if we just use resistance, I is equal to V over R. So what happens if you double the resistance and you don't change the voltage? Current is going to do what? Current is going to half. So we say current and resistance are inversely proportional, which means they do what? Yeah, but by the exact same amount. So if I double the voltage over here, voltage is on top. So if I double the voltage and I don't change the resistance, if I push a car twice as hard, it's going to move. If I don't change the weight of the car, it's going to move twice as fast, right? That makes sense. So what will be the current in a circuit? So here's our formulas, right? So I is equal to what? V over R. R is equal to what? V over I. And then V is equal to I times, we'll use R here. So what will be the current in a circuit with 100 ohm? And by the way, I need to put that on the supplies. What do y'all have to have in this class? Need to add that to your list of supplies. Need to have a calculator. And you need to have a scientific calculator if you're in this trade. Because we're going to be dealing, in your studies here, we're going to be dealing with engineering notation, exponents. Scientific calculator does exponents. Now, if you got Windows up, you can use a Windows calculator. We don't let you, during tests, we don't let you use a cell phone. Why don't we let you use a cell phone? Because you can look everything up, right? Because you got access to the internet. So that's why we require you to have a calculator. A Texas Instrument 30X is perfect. It's like $8. It's a cheap calculator. And that would be everything you need to get through all the classes that you're going to take in our program. That calculator would be fine. So today you can go ahead and use your calculator on your phone. So we'd say what? We would say current, I, would be equal to V. What's my V? 50 divided by 100. By the way, we don't put any We don't put it. This is a law of electricity, by the way, that we refer to as Ohm's law. This is the way. And that's uppercase. Ohms. This is the name of a guy. It's the last name. This is what we call Ohm's law. So we have three things that controls the amount of power in a circuit. We have voltage, we have current, and we have opposition. If I don't have any one of those, I don't have any power. Does that make sense? We've got to have these three. Ohm's law tells us the relationship of those three quantities. And when you get out in the field, you might not ever write Ohm's law down, but if you know Ohm's law, you understand the effects of what things happen, why things happen, because one of these things right here changed. Why does this thing keep burning up? Why does these light bulbs keep glowing? Why does this happen? Why does that happen? Well, if you understand this law right here, you will understand what's going on, and it will give you a good indication of what you need to do to repair the house repair something before your house burns down, right? You'll understand. And this is Ohm's law. Ohm's law itself, written out, is long and tedious, but basically it gives us the relationship between the what? The voltage, the current, and the opposition in a circuit. You've got to have all three of those to have circuit. I mean, good gracious, if I come out and buy 10,000 miles of conductors, those conductors are not going to do any good unless I hook them up to a what? Unless I hook them up to a source and I hook it up to a load. And then they do what they were intended to do. Of course, I could take it and sell it down here to Morris Coal Yard, right? Scrap it. So we would say, okay, what would be the current? So what would happen to the current? So let's say the current, we got 100 ohms worth of opposition. We got 50 volts pushing into that opposition. And the current is going to be a what? So if you got your calculator, on your phone, that's fine. If you don't, what's that? Yeah, it's going to be 0.5 amps, or technically we refer to that as 500 milliamps. And we're not going to learn engineering notation in this class, but you get that in intro to, are you in intro, Anthony? Anthony, are you asleep? Are you asleep in my class? Are you taking intro to engineering this semester? Are you taking EET 100 this semester? You'll get into engineering notation in that class. By the way, don't sleep in my class. You know, if you want to stand up, that's fine. I found out a long time humans has problems sleeping standing up. They're not like cows. You know, cows can go to sleep standing up. Anybody ever been cow tipping? You know what cow tipping is, right? Huh? Yeah, cows will be sound asleep, but we're standing up. And you walk out there and you bump them, they'll just fall over. Call it cow tipping. So 0.5 amps. Well, now that I know that current and opposition are inversely proportional, then if I half the resistance, so if I go down to 50 ohms, then my current would go up to 1 amp. Because I half the resistance, my current double. Because they are inversely proportional. You could do the math, but I can see 50 divided by 50. I can do that in my head, and it comes up and gives me what? 1. If I come up here and double the resistance, then I would go down to 0.25 amps. Because they're what? They're inversely proportional. So now I understand that if I double the opposition in a circuit, the current is going to be half. If I half the opposition in a current circuit, the current is going to double. Right? You understand? So let's go back to I is equal to 50 over 100. What if I doubled my voltage? Well, then I would be equal, and I'm going to leave my resistance alone. Well, over here, voltage is on the top. Over here, I is on the top, right? We assume it's to be over 1. So that means they are directly proportional. Now what directly means is they change exactly the same ratio, right? So if I come over here and make this 100 volts, and I leave this at 100 ohms, over here my current was 0.5, over here it went up to 1 again. So I doubled my voltage to the circuit, and what happened to the current? The current did what? Double. Y'all understand that? This is why voltage is so important. You know, this is why if I have a light bulb that's rated for 120 volts or 110 volts, and I put it into a 120 volt circuit, it blows up quite twice, because now the bulb is conducting twice the amount of current, right? You understand that? And it's not designed to handle that much current, so what does it do? It would blow instantly, yeah, because we double the voltage. And of course, if I half the voltage, so if I take this and put it into a 60 volt circuit, it's only getting half the current, and it's going to be doing a lot less work, right? You understand? So what would be the resistance that would allow 15 milliamps of current to flow in with an 80 volt force? So I is equal to what? I'm sorry, so R would be equal to V over I. So R would be equal to, what do we say? 85 volts divided by 15 milliamps, which is 0.015. What's that? Yeah, we're not, in this class we won't use engineering notation right now because Anthony hadn't had intro. So 5,700 ohms. Are we okay? Or what we would say 5.7 kilo ohms. And y'all get into engineering notation really fast in that class. What voltage is required to cause 10 amps of current flow to 150 ohms? So V is equal to what? I, so it'd be 10 times R, which is 150. By the way, in these formulas, we don't put these units because that would give you weird, in algebra, they would freak out. So what we're doing, we're dealing with proportions. This is proportional to that. So what would we end up, what would be the voltage required? By the way, over here on I, what's I equal to? It's equal to V over R or over ohms. Okay. And we came up with 0.5 amps. When I double the voltage, what did I do with the current? It's on top. It doubled, right? Which gives people a lot of problems because power is equal to what? V times I. So what happens to the current if I double the voltage to a circuit? So what happens to current if I double the voltage to the circuit? It doubles. So what happens with power if I double the voltage to a circuit? No, it don't. So let's do this. Let's start off. Let's say I say, okay, by power. Okay, let's say I have 10 volts at 10 amps. What's that equal to? 100 watts. Let's double my voltage. What will my voltage go to? 20 volts. But if I double my voltage to a circuit, what happens to the current? It doubles. So that means it would go to 20 and my power would go up to 400 watts. So power varies with the square of the voltage. It's not proportional. This is why if I double the voltage to a light bulb and it's a 100 watt light bulb, it's going to try to produce 400 watts worth of work. And that's what burns it up, right? You understand? Is that 400 watts worth of work, and it only can do what? It only can do 100 watts worth of work. So power varies with the square of the voltage. If you double the voltage, the power decreases by a factor of 4. If you quadruple the voltage, then the power goes up by a factor of 16. If you half the voltage, power goes down to 1/4. And this is why if you've got a light bulb that's rated at 50 volts and you put it on 25 volts, you're not even going to see it come on because it's doing 1/4 of the work, right? You understand? So power does not vary with voltage. It does not vary. It varies with the square of the voltage, right? You understand? If it goes up, it's times the square. If it goes down, it's 1/over the square. And that's why it don't take much voltage drop to cause big problems in a circuit. In an ideal circuit, all the push provided by the voltage source will be distributed across the loads. Current flowing through the opposition of the loads produce work that the circuit was designed to deliver. So we don't get work unless we have current flow. And that current has to flow through a load, right? In a real circuit, all devices have some resistance and some reactance. Even conductors have resistance and reactance. And that's what I needed to run off. The amount of resistance R a conductor exhibits to the flow of current is determined by what? What's the 4 main things that determine? The second one shouldn't even be in the list because the second one changes this. So insulation. So in the wintertime, we wear coats. Why do we wear coats? To keep us warm. So insulation will keep a conductor warm. So there's 4 things that determines the amount of opposition a conductor has. Now we would like the conductor to have how much opposition? None. 0 ohms. Right? If it has 0 ohms, it will do no work. All it'll do in life is carry current. So the 4 things, what determines the 4 things? The material it's made out of, the size of the conductor, the length of the conductor, and the temperature that the conductor operates. Metals, when metals get hot, their opposition goes up. When metals go down, their opposition goes down. This is why when they start talking about superconductors, which are conductors that have almost no opposition at all, they put those suckers in liquid nitrogen to get the temperature down real low so the resistance of the conductor will go down what? Now you're not going to see a superconductor unless you work for NASA or maybe get into the military on some of those ships that got superconductors in them. We're going to deal with metal conductors or optical conductors. Right now we're talking about copper. All conductors that we're going to deal with has resistance. If I put current through resistance, we're going to have a voltage drop. If I have a voltage drop and I have current, then I have power. And this is resistance. Resistance releases power in the form of heat. So conductors, real high current conductors, will get warm. So this is why if you go into electrical classes, they'll talk about size of conductors, and we have to do certain things. So that's for a normal size house. If I'm going to run that conductor, 500 feet out to a light in my backyard, then I'm going to have to increase the size of the conductor, right? You understand? Because to compensate for the, we had a guy that had a compressor, portable compressor, was on wheels. He bought him an extension cord. He bought an extension cord that had, I think it was 16 gauge wiring, so it was a real cheap extension cord. And he plugged it in his compressor, and he couldn't figure why his compressor wouldn't run. Because what was happening? The resistance of that extension cord was enough that when you tried to pull that current that was required to run the compressor, it wouldn't, the actual wiring was dropping the voltage. The amount of reactance is determined by the frequency. So we'll have to understand this. Alabama Power, we're not concerned with this so much because the frequencies are so low. When we get into communication cables, you know, like Ethernet cables, these cables you see up on there, information is flowing on there at 1 million cycles per second. I'm sorry, 100 megahertz. So that's 100 million cycles per second. Well, that's an extremely high frequency, so we're going to have to really understand this thing we call reactance when we start dealing with communication cables and why you can't do things. So, and we'll talk about it later on. I'll tell you my story about my father-in-law and his cable coming into his house. When current flows in and out of opposition, the amount of push available to the load is decreased, and we call this a watt. We call this a voltage drop. Electricians call it line loss. So if you ever heard about people like Alabama Power start talking about line loss, that's what they're talking about. That's loss, voltage loss over the actual transmission cable itself. And the problem is if we have a lot of voltage drop, remember, power varies with the square of the voltage. So if the voltage halves, then you're going to be able to deliver only 1/4 of the power that the load needs. So I either got to do what? I got to figure out what material I need to use, and then I got to make sure I use the right size for the watt. The length that conductor is going to have to run. And then I've got to determine how much current that guy can handle depending on what temperature is designed to run. And we'll look at the actual charts that the National Electrical Code sets up for electricians to actually size their conductors. And it deals with 3 things. It deals with what temperature is it going to run at, what material I'm using. Of course, the NEC cables are set up for copper. And a rule of thumb is that if you go to aluminum, you use the next bigger wire get the size. So you go up to the next standard size. So the NEC tables are okay. It's just that if you know that and you want to use aluminum. Of course, we don't use aluminum much in houses. And we'll talk about why. The amount of voltage drop can be calculated by the formula V is equal to I times ohms. So if I know the opposition of the cable and I know the current that I'm trying to conduct, then I can get calculate the voltage drop across my wire, right? If that is unacceptable for what load I'm trying to run, then what would I probably need to do? I would probably need to go up to a bigger size conductor. So this is an ideal circuit right here. And this right here is a true circuit. And of course, what I'm trying to choose is I'm trying to choose the smallest conductor I can possibly choose. Why? Yeah, because of cost. You know, I could go in my house and run 6-gauge wire all through my house. I probably wouldn't have any trouble with it, but I'd be spending a fortune just for the wire, right? So what we're trying to do is we're trying to size a conductor, the smallest conductor I can use, and support the load that those conductors are trying to run. So this is what we call the American wire gauge. It assigns a number to a gauge. So when we talk about a bigger gauge or a smaller gauge, we're talking about the actual physical size of the wire, but the gauge numbers actually, the smaller the gauge number, the bigger the wire. And there's a formula for this, by the way, that we're not going to, I'll show you. So the American wire gauge, this gauge goes all the way from what we call a 50, a wire gauge number 50, all the way up to a wire number called 4/0, AUGHT. So that's a term. If you ever watched the Beverly Hillbillies years and years ago, Jethro called zeros aughts. So aught, AUGHT, is another name for a zero. So we would refer to this as a 4/0 conductor. And it has a diameter of 0.46 inches, which would be a little less than half an inch. Yeah, probably, no, it's still not a half inch. Half inch would probably be, what about right there? So this guy here has half inch. And that's as far as American wire gauge goes. Above that, we actually use something we call KC Mills, which we'll look at in a minute. So when we tell y'all in electronics that you need to buy some 22 gauge solid strand wire, then this would be the actual diameter of the wire. And this would be the gauge in millimeters. Of course, over here we're still using inches, but the American wire gauge would also apply to a European standard too. But they wouldn't give the sizes in inches. They would give the size in millimeters. And then anything above 4/0 over in Europe, they call it millimeter squared is what they call it. And we'll talk about that in a minute. So house wiring, we use a standard 14 gauge wire. This is amperes, but notice what this says. This is 20 degrees centigrade. 20 degrees centigrade, which is, what would it be? 0.8. It'd be about 60, a little less than 70 degrees. And free air, so that means the ampacity of a 14 gauge wire is rated at 32 amps if you operate it in a 20 degree centigrade environment without any insulation on it at all. If the temperature goes up, it would be no longer rated at 32 amps. If the temperature goes down, you could actually put more current in it, right? You understand that? And if you didn't put any insulation on it, you ever wonder why? Yeah, of course, you can see it's going to save a lot of money, but this is why power lines are not insulated. So your power lines up on your power pole are not insulated, because if they insulated them, they would be a heck of a lot safer, right? You understand? We wouldn't ever have to have them worry about them touching together. This happens all the time. Out at the house, we have a 3-phase power line not far from my house. You know, them fell over it. Well, when it did, it took this one and knocked it down against one of the phases. The phases were vertical instead of parallel. Man, it created all types of arcs and sparks and burning. If they were insulated, they wouldn't have to worry about that. You wouldn't have to worry about trees falling across power lines and creating shorts, right? You understand, which happens all the time. But why don't they insulate them? Well, they don't insulate them because if they insulate them, the ampacity, the current carrying capability of all those conductors would go down. So they would have to use a wall. They would have to use bigger wire gauges just to insulate them, which would cost the power company so much money. So they just put them up high enough so only idiots can climb up there and get into them. There's some videos on YouTube where I think it's over like in India stuff. Most of the trains over there are electric powered. They got the wires up there, and they have so many people they climb up on top of those things. And every once in a while, they'll reach up there and grab that power line up there. It's not pretty. So anything below 4/0 is going to be given in a gauge number over here in the U.S. Anything above 4/0 is going to be given in something called circular mills. Okay? This makes sense? So we got to understand gauge numbers. And another thing this chart shows is also the resistance per 1,000 feet. So a 14 gauge wire would have what? So we use two main wires in our house. We use usually three, but the two main we use is 12 gauge. So when I run a 240 volt service, we run it with 12 gauge. If I run a 115 volt circuit, we run it on 14 gauge. So what's the ampacity of a 14 gauge wire? 32 amps. But it has 2.52 ohms per thousand feet. They rate it at 32 amps, but it has 5.525 ohms per 1,000 feet, or let's just say 2.5 ohms per 1,000 feet. This is copper. So if I ran it 2,000 feet, then that's going to be 5 ohms, right? If I tried to put 10 amps through 5 ohms, it's going to drop 50 volts. The wire would drop 50 volts. That means if I was trying to run 2,000 feet of 14 gauge wire and hook up a light out here or hook up a load out here that required 10 amps, then I'm only going to get 70 volts out there. And it's not going to do near the work because power varies with the square, right? Y'all understand that? So just because you half the voltage, if we half the voltage to a device, the work that it does is going to drop down to 1/4. That would be like me going out on my car and killing, it's a 4-cylinder, killing two of the spark plugs. Now my car probably wouldn't create enough force to even pull off from a red light, right? You see these cars that misfire, just use 1 cylinder, and they have problems even starting off from a red light because power varies with the square, right? You understand that? So if I lose one spark plug, we're going to lose that much power out of our circuit. Do these all the time. Work, the formula for calculating power, electrical power. The main formula is V times I. But one of our laws of electricity, of course, is, watch that out for me. So if y'all see that little arrow popping up like that in the center, what does that mean? Yeah, the problem is when the little thing pops up here before I can pause the recording, it covers up my pencil that I use to draw on my PowerPoint. So what would be the power, what power is produced by a load with 10 amps of current and 60 volts of push? So power would be equal to V. What's V? And what's my current? 10. So what would be our power? Yeah, power is rated in watts. What power is produced in a load that has 100 ohms of resistance and 50 volts applied? So that's V squared, so that'd be 50 squared divided by 133. This is why you need a scientific calculator, is that just standard calculators usually don't have the square function. Anybody got it? I don't know, 18.8. Anybody else got something different? I don't have my calculator. So 50 squared divided by 133, 18.8 watts. What power is produced by a load of 5 amps and a current of 32, and 32 ohms resistance? So I squared, that'd be 5 squared times 33. Five squared times 33. Oops. So I said 25 then. Oh, no, that was after the square. 5 squared times 33. 125 watts. And anytime we use these formulas, by the way, they probably won't be on the test that I know of, but later on when we start getting into communication cables, right now we understand that if a wire has an ohm and I use the wrong size, so if we go back here and look, if I'm running, if I'm only going a little small distance, this right here, and I'm trying to do 5 amps, I might be able to drop down to a 20 gauge wire because it only has 7/10 of an ohm, right? You understand? So that guy would only be dropping about 1.5 volts over the length of the wire. Or I might be able, this table is set up in both inches and millimeters, and over here kilometers. And you need to really start dealing with the metric units of measurement, because slowly but surely everything is doing wrong. So, years ago, so now you can't work on a new car unless you got a set of metric wrenches. So cars are moving toward the metrics, and that's even if they're made here in the United States. About the only thing that still uses the standard SAE is the lug nuts on the car now. Those are still standard sizes. But every other bolt in a car now is going to be metric. Power in relationship to current, we've already talked about that. If voltage and current are directly proportional, if the voltage doubles to a circuit, if the voltage to a circuit doubles, then what's going to happen? Then the current's going to double, and the power is going to increase by a factor of 4. If the voltage to a circuit halves, then the current's going to halve, and the power would decrease by 1/4. So power varies with the square. You'll understand that. Are we okay there? If 5 volts is applied to a 5 ohm resistor, what will the current be? So we'll come over here and we'll say, okay, 5 volts, 5 ohms. I would be equal to V over R. So that's going to be 5 amps. We can do that in our head, right? If the voltage to the circuit doubles, what will be the new current? So it's going to be I is equal to 10 over 1. I didn't change the ohms. So what happened to the current? Current. So up here I said 5 divided by 5. So up here power would be 5 times 5. That's going to be 25 watts. Down here my voltage went to 10. My current goes to 10. That's 100 watts. So what did the power do? When I doubled the voltage, the power went up by a factor of what? 4, which would be 2 squared. If the voltage applied to the one goes down, so let's go down. So up here I had 5 amps. I'm on half the voltage. So I would be equal to V over R. So now it goes to 2.5, right? Y'all understand that? Then when I calculate my power, that's going to be power is equal to 2.5 times 2.5. What's that? Huh? What's that? All right. I guess it is. 2.5 times 2.5 is 5. 2.5 times 2.5 is your right. It's 6.25. Which should be exactly what? 1/4 of that. So if you take 25 and divide it by 4, what should that give you? Should come up and give you 6.25. The previous problem, of course, we've already worked this. When the voltage double, the current double, which caused the power to increase by a factor of what? 4, t squared. In the previous problem, when the voltage decreased by a factor of 2, the current decreased by a factor of 2, which caused the power to decrease by a factor of 4. But it's going down, so it's going to be 1 over squared, right? The power increases and decreases by the square of the voltage. So here's all the power formulas, which we're not really interested in. These are all these over here transposed. This is very important for us to understand. Y'all go ahead and take another break, and then we'll finish up today. This in cable slides and, of course, in insulation, it's very important that you understand shorts and opens. And the short is probably one of the most misused terms for people that don't understand electricity. You know, God bless my mother. She's gone now, but she uses, oh, I got a short. I got a short. People say, I got a short somewhere. Usually they're talking about an open. Shorts are bad. A short is an undesirable path for current to flow. So you still have current flowing. It's just not flowing in the path that it was intended to flow. Shorts will decrease the amount of resistance in a circuit, which will cause the total current in the circuit to increase. A short circuit occurs when the source conductor and the return conductor come in contact with each other, which will bypass the resistance of the loads. So the only thing you have in limiting the resistance of the circuit. So if I, according to Ohm's law, if I is equal to V over R, if I and R goes to 0, then what's our current going to be? Yeah, if you divide by 0, every calculator is going to give you an overflow or going to give you an error because why? Anthony. Most of the time I can put this on a test and I can say, you know, if you have 0 ohms in the circuit, how much current you'll have, and somebody in that class is going to say 0. When in actuality, if you divide by 0, your calculator can't divide by 0. Because what is division? Do y'all know what division is? When we first got into computers, the first processors that came out could not divide. They could do 2 math things. They could do addition and they could do subtraction. Well, addition and subtraction is the base of all math. We're not talking about formulas. We're talking about math. So what is division? Well, division, if I wanted to take 25 and divide it by 5, what I would do is I would start subtracting 5. And what would I come up and get? I would get 20. Then I would subtract 5 and I would get what? 15. Then I would subtract 5 and I would get 10. Then I would subtract 5 and then I would get 5. Then I would subtract 5 and I would get 0. And then I would subtract 5 and I would get an overflow, which means I've subtracted as many as I can. I would count the number of times I subtracted, and that would give me, I've subtracted 5 times, right? You understand, before I generated a borrow from nothing. Well, if I say 5 divided by 0, if I say 5 minus 0 comes up with 5, 5 minus 0 comes up with 5, how many times can I subtract 0 from a number before I generate a borrow? Forever. So any number divided by 0 is what we call infinity. Since your calculator cannot do infinity, it comes up and shows you an error. So take your phone out and ask Siri what's 1 divided by 0. Or 0 divided by 0 is the response. So I come over my calculator, I'm going to say 5 divided by 0. And it says what? It cannot, so my calculator cannot display infinity. So it says I cannot do that, right? You understand? So 0 divided by, so according to this, according to Ohm's law, if I had a short circuit, which means I come over here, normally we come over here and we have our voltage source, and then I come over here and go to a resistor. Well, a short circuit means I connect there to there. And what did I lose? I lose the R of the load. So now it says, okay, if those wires had 0 resistance, it means I'm taking V divided by 0, and my current would go to infinity. Well, Alabama Power cannot produce infinite current. So what's going to happen? Somebody is going to give up. Somebody is going to give up, right? You understand? Either your voltage source is going to give up or your conductors are going to give up. One of the two is going to give up the ghost. Now, if I've got a little AA battery and a AAA battery and I put a little wire across it, you know, and short it out, if you put a voltmeter across the battery, the output of the battery would drop to 0 because the internal resistance of the battery is dropping the voltage. If I go out to my car alternator, which is a regulated power supply, which means if the resistance goes down, it automatically raises the voltage, and you short out that sucker, you're going to be in big trouble if you don't have a fuse. So there is a fuse in your alternator lead. So somebody's going to give up, right? You understand? If we have a short circuit, somebody gives up. Either the voltage source gives up or the conductors give up. Now the problem is, if we have conductors out there, what happens is my voltage will drop down because your power supply can't do that. It's going to pump out a ton of current. Okay, so the wires start warming up. Well, when the wires start warming up, their resistance goes up, which means it seems like current will go down, but now all of a sudden the battery can support that current. So the output of the battery starts going back up because now it can support the current. So what happens is R goes up, I goes up, you create a lot of heat in your wires. What are your wires going to do? They're made out of metal. What are they going to do? They're going to melt. Or either they're going to catch your house on fire if they don't melt. When I was in the service, I had a Vega GT. A Vega GT had a hatchback. It was a hatchback. And so you could see all the way back into the trunk. And we pulled a trailer out to California, a U-Haul trailer, and I tapped into the wiring on my tail lights. Well, when I got out there, stupid me, I didn't disconnect it, and I had a dog chain in the back that one of the wires got against, and then it went over to across the carpet over to the ground, or common on call. And the dog collar had enough resistance in it, because it was a chain, that it didn't blow the fuse. But it created a lot of work, got red hot, and caught the carpet on the back of my car. So I was driving along, and my lights got dim, and I said, okay, and then it dimmed again, and then all of a sudden I saw something flashing in my rearview mirror, and I looked back in my rearview mirror, and it's flames in the back of my car. I pulled off on the side of the road, started running away from it, and then I started thinking, Rich, this is the only car you got. You might as well try to save it. So I went in and popped it open and jerked the carpet out. Saved my car, burned my hands a little bit. But what would happen then, I didn't have a real, what was happening is the resistance of the conductor was enough to do what? It wasn't enough to blow the fuse, but it was enough to cause that chain to get extremely hot. So what's going to happen, you got to understand, if somebody don't give, somebody's going to eventually give up if you have a short circuit. If we have a short, it's going to cause the conductors to go up, but it's not necessarily going to blow a fuse. So shorts are really dangerous. So this is why we have a short circuit. All circuits must have resistance. If not, according to Ohm's law, it says the current in the circuit will try to go to infinity. It cannot go to infinity, right? Since power is equal to V times I, it's going to try to produce infinite amount of power, but it can't do that. Of course, the current flow will never go to infinity. If the load is bypassed, the current flow in the circuit will be limited only by the what? The resistance of the conductor and the internal resistance of the voltage source. You go out there on your car battery, by George, which has almost no internal resistance. You short that sucker out, that battery's probably going to blow up on it. It's going to create so much heat inside the battery, it will probably blow up on it. You don't want a car battery blowing up on it, because not only are you dealing with all this garbage flying at you, you got all that acid coming at you too, right? You understand? So never short out a car battery. If not protected by an overcurrent device, somebody's going to give up. And overcurrent, what's the two main overcurrent protection devices we use? Fuses and circuit breakers. And they're designed to trip or open the circuit if you have too much current flow. When current flows through, resistance of the electrical conductor, heat is generated. When metals are heated, their resistance goes up. When resistance goes up, more heat is generated from conductor. If something does not limit or stop the current flow in a circuit, the conductors will get extremely hard and hot and may eventually melt and catch on fire. But, or the source might catch on fire. Somebody's going to give up the ghost, right, on short circuit. Two devices used to stop the current when predetermined levels is exceeded are fuses and circuit breakers. Any device that protects a circuit from a short is referred to as an overcurrent protection device. So these are fuses and circuit breakers. These are commercial or residential circuit breakers, which everybody sees. And these are examples of fuses. What advantage does a fuse have over a circuit breaker? Yeah, a lot cheaper. So when you get out in industry, you're going to see a lot of fuses. A lot of fuses. What advantage does a circuit breaker have over a fuse? Yeah, you can reset it. So that's the main advantage, but they cost. Go down to Lowe's and look up a 15 amp fuse rated at 125 volts and look at a 15 amp circuit breaker rated at 125 volts. And you'll see the difference. So commercial applications and user applications, we'll probably see a lot of circuit breakers. In industrial applications, you'll see a lot of fuses. So here's a short. So notice what I did is I decreased the resistance to this load right here. Now this load right here is going to try to make up the difference. This guy was dropping voltage. It's no longer dropping voltage. All the voltage will apply by that load. The power consumed by that load is going to go up. So a short could cause other devices to fail. But it might not necessarily blow a fuse. Your fuse does not protect against shorts. Your fuse protects against short circuits. So when a fuse NEC rates a 14 gauge wire, a 14 gauge conductor. They rate it at, even though it'll handle 32 ounce, NEC rates a 14 gauge conductor as 15 ounce. Because what they're doing is they're saying, okay, in this house, this is going to be ran through the wall, or it might be run through the ceiling, and it's going to get very, very hot. It's going to be inside insulation. It's going to be inside a jacket. So that means that heat in that conductor is going to stay in there. So every time we run the conductor through a higher heat, we have to drop the ampacity. So why NEC rates a 14 gauge conductor at 15 ounce is they're considering just about every worst case scenario that conductor can rate at. What's the circuit breaker rated at? The circuit breaker on a 14 gauge wire in residential is rated at 15 ounce, which is the current carrying capabilities of the conductor, not the load. You understand? So this is why they say don't run extension cords under carpets, because an extension cord is not designed to handle a lot of current. It has a pretty good deal of resistance. You could literally touch the two wires of a long extension cord together, and the wire has enough resistance not to pop the breaker. Because the breaker is not looking for a short, it's looking for a short circuit. Right? You understand that? So yeah, you get that short out there on that long extension cord, you can catch your house on fire real easy, and your circuit breakers won't ever even trip. So this guy right here is going to have big problems, because now it's going to be trying to produce, if these two had the same opposition, it's going to be trying to produce 4 times its work. Which is going to happen. It's either it's going to get extremely hot, or it's going to do what? It's going to burn up. So shorts could cause devices to open. So that's a short. This would be a short. This would be a short. This would be a short circuit. Short circuits are really bad. So what the problem is we can have a short, so your TV can burn up and not even hurt galvanized power. I mean, I've had TVs, I've seen smoke come up the back. Well, what caused it to smoke? It probably got a short in there somewhere, right? You understand? But it didn't pop the breaker, because it wasn't a short circuit. It was a what? It was a short. And that's what happened to me on my car. I didn't get a short circuit. I got a short, because the dog collar was not being considered. The dog chain was not being considered as a conductor. It was being considered as a load. To prevent shorts and short circuits, it is imperative that the conductors in a circuit are isolated from one another. The substance that isolates the conductors is called an insulator. Insulators are made from substances that exhibit extremely high opposition to the flow of current. So now you know the function of the insulator. So this is a conductor, right? And what's this yellow thing up there? That's the insulator. What does that insulator do? It keeps it from touching other conductors and creating short circuits, right? You understand? So that's the function of the insulator. So what I can do is I can take these two wires and I can touch them together, and they're not going to short circuit. That's why when you look at all these conductors in your house, they're all going to be insulated. Except when it comes to the point where you got to splice them or do what? Terminate them. And of course, you got to be real careful when you terminate, because if you leave too much exposed wire, then you could get what? Short circuits very easy. Very easy. Or if you don't cut off enough insulation, and if you get the insulation up under the screw, you might not create a good connection. Opens. An open. So that's it for that. So we'll start on Wednesday. We'll come back and start looking at opens. But we have to be real careful when we do these splices and these terminations and all this other kind of stuff. We have to know what we're doing, because we could very easily create shorts, or we create if I connect the wire if I terminate the wire to the wrong spot, which happens a lot. One of the things they did in troubleshooting at the Siemens thing was all they did was just connect wires to the wrong spot. And that happens all the time. You know, you got electricians going out there wiring up stuff. They take something off and they forget how they wire. They say, you know, I'll remember how to do this. And then they'll go on a lunch break or something, or they talk to their buddy for a second and they turn around and they forget how that thing came off there. And they say, well, it's just 2 wires. And they get them back, they hook them up backwards. Well, what could you have just done? Well, you could have just created a short circuit. So a lot of the problems they did was just standard problems. They just moved wires around. They connected them to the wrong spots. Of course, they knew what they was doing, and they didn't create shorts. Okay, guys, see y'all Wednesday. Everybody got the syllabus for you.